This is Lecture 9E on the equations of motion with resistance for Calculus 2. The way you derive the terminal velocity is that you must include all the forces to which the object is subjected. And these will include your external force that we always did, for example, a wind or a motor or the propellant in a pop bottle rocket. We include the force due to gravity, fine. And now we must include this new set of forces, which are forces that resist motion. This can be friction for motion, an object moving over a surface, or if it's moving through a fluid, you have water resistance if the fluid's water, air resistance if the fluid's air, and then you also have buoyancy. Something that we haven't encountered before that is common in these resistive forces is that they are not constant. Instead, they depend on the velocity. So the faster you go, the more these forces act against you. And I'm going to list here 3 types of models. Of course, there are many more. Let's consider that the velocity is always positive, so I can get rid of those absolute value signs. But in one model, the resistive force is just proportional to the velocity. Another model, the resistive force is proportional to the velocity squared. This would give more of a resistance than the first model. And a weaker model, the force is proportional. K is a constant proportionality, and it's proportional to the square root of the velocity. Right. The K in all these equations is not the same. I just wrote it there to be some constant. The resistive force equals some constant times the velocity, or some constant times the velocity squared, or some constant times the square root of velocity. This is probably the most realistic model. The resistive force is proportional to the velocity squared. I'm going to run through a couple examples. The first is a calculation of terminal velocity. This is the velocity of say something that's, here's the Earth. Okay, here's this projectile coming down through the air. It could be someone in a parachute or some bullet. It doesn't matter what it is, something falling, some falling object. Okay, I'm going to write the equation for this. I'm going to put here the forces. I'm going to list all the forces. I'll do it in a different direction than I've done there. Here's a force due to gravity. It's pulling you down, but there's a resistive force due to the air, and that's acting in this direction. So here's your force due to gravity this way. The resistive force is in this direction, so that's why I have the negative sign. And force, as we know, equals mass times acceleration, or I can write that it's mass times dv by dt, because I'm going to integrate. So let's write that equation out again. Mass times dv by dt equals the force due to gravity, and that's heading down, so it's mg. And then there's another force proportional, let's say it's just proportional to velocity, we'll use that model, kv. K is some constant of proportionality. This is your air resistance. This is the force due to gravity, and this is just mass times acceleration. So what we have here, it's written out right here. This is a differential equation. What kind is it? Okay, it's first order, because the highest derivative is the first derivative. It's an ordinary differential equation because there's only one independent variable, and that's time, t. It's autonomous because t does not appear explicitly in this equation. It is separable, so we can solve it by that method. It could also be solved by using an integrating factor. I'm going to solve it using an integrating factor. To do that, I have to put the equation in standard form. If you recall the standard form, I'm going to use y as a dependent variable. The standard form for the, I'll use t. For use of an integrating factor, you have to write it like this, equals, or you can write, actually I should have written a and b. I think we're used to writing a and b, but it doesn't matter whichever you want to use. Okay, so here's the standard form. I want the first derivative by itself. I did that. Then I want the function right here, multiplied by something that only depends on the function. Well, a constant works well. That's fine. And on the left-hand side, all right, made a total mess of this. Let me start that over. Here is the standard form for the differential equation when you're going to use an integrating factor. There. I think I did it right this time. Okay, first derivative by itself. And that's dv by dt. V is my function. Here's my v here. It's equivalent to the y in this equation. It's multiplied by k over m, which is a constant. That's fine. That's going to become my a. And on the other side is my b, which is g, just the acceleration due to gravity. From this, I developed the integrating factor. The integrating factor is e to the minus integral of a dt. In this case, plus, I'm in good shape today, a is k over m dt. K over m is just a constant, so carrying out that integration, I just get k over m, the constant, times t. And that's the integrating factor right here. You can apply to both sides. You understand that on the left-hand side, you can write this in terms of the product rule for differentiation, do some integration, and here is the solution. I'm not going to carry out all those steps again. The solution will look like this. I'm going to use this one here just to show you. You end up with y equals a e to the negative integral of a dt times the integral of e a dt, and you're integrating that, times b dt. All right. Now I've just put that together. I need the b. B in this case is the g. You see where it appears right here. Now I need my integrating factor. Okay, I already carried out the integration over here, so I know what it is. I just use that. And then it's multiplied by e minus that integral. That is green, so that's just here. And I see this equation is lacking a dt, so I'll put it in now. All right. So I was able to put this equation in standard form. Then I used an integrating factor, and I solved it. Since the acceleration due to gravity is a constant, that comes out from under the integral sign. It's easy to evaluate the remaining exponential, and this is what we get right here. Rearranging gives this familiar form. If you've been following through these lectures on the different differential equations, you'll recognize this form right off. What do we have here? Well, first, here's the velocities, what we solved. We have a steady state term, and then we have a transient term. The steady state term will be our terminal velocity. On the other slide, I solved for the particular solution where with the initial velocity of v0. And what is v0? Well, if it's a bolt that fell off something and the object wasn't moving up or down, then that would be 0. If it's projected, thrown down some way, then that would be the velocity at which it was projected down. If a person jumped out of the airplane with force or was pushed out, then that's the initial velocity. Okay, so I've got that in this equation, and here is my final solution. And what I used for the model of the resistive force, the resistive force was proportional to the velocity. I used that for air resistance. And now look what I have. I've got those two terms again. The first term here is my steady state equilibrium term. It is called the terminal velocity. The other is this decaying exponential. It is the transient. So we've seen this before. When we find these solutions, we'll see a steady state term. If we look at this graphically, this is the equilibrium. Then we see the decaying exponential. Now I'm going to run through the same problem, but I'm going to use a different model for the resistive force. Remember, there were three models that I showed you before. In one case, the resistive force was proportional to the velocity. That's what we just did. Then there was another one in which the resistive force was proportional to the velocity squared. That's what we're going to do now. There was a third one, which we're not going to do. The resistive force is proportional to the square root of the velocity. This is the one we're going to do right now. So when I have mass times acceleration equals force, then including all forces, I will have the force due to gravity, right? And then I will have a resistive force. Signs are an issue. Okay, let's go ahead and just work through this. V greater than 0 means the object is falling. That's a convention that I've adopted that other people do. I can't say I'm especially fond of it, but I went ahead and used it anyway. Okay, so acceleration is the time rate of change of velocity, so we have that here. Here is our force due to gravity pulling us down in the direction of increasing velocity, and the resistive force of minus k times v squared is acting in the upward direction. This is a very interesting equation. This is one we have not solved before. What kind of equation is it? It's first order, because the highest derivative is the first derivative. It is an ordinary differential equation because there's only one independent variable, and that's time. It's autonomous because time does not appear by itself in any of this throughout the equation, anywhere in the equation. However, it is nonlinear. Why is it nonlinear? Because the function itself, v, appears to the second power. For a linear equation, all the derivatives have to appear to first power only, and they cannot be multiplied or divided together. So here we have a nonlinear equation. We can look at this graphically, since our methods are for linear equations. Okay, well, we could have solved it as a separable equation, but the integrating factor is used for linear equations. So let's look at this analytically. Graphically. Right? We want the equilibrium solution because that will be our terminal velocity. At equilibrium, for the equilibrium solution, the first derivative is 0. So here's our equation. I'll write it right down here. dv by dt equals, and I can divide through by mass, and I get g minus that constant for the resistive force times v squared. I need this equal to 0 for the terminal velocity, for the equilibrium solution. Solving, I find that the terminal velocity is equal to the square root of acceleration due to gravity times the mass divided by the constant for the resistive force. So you see here we can find a lot about a solution just by looking at it graphically, even if we can't solve it analytically right off. So let's look at the results. If the resistive force was proportional to velocity, then the terminal velocity is gm divided by k. If the resistive force is proportional to velocity squared, then the terminal velocity is less. These are all positive values, so the square root of them would be less than the terminal velocity for the other resistive force. This is a stronger resistive force. And again, the k in both equations is not necessarily the same. I just use it so we didn't have too many letters running around. The more realistic model, the one that seems to dominate in practice, is this model right here. Okay, so to summarize what we did is we wanted to find the terminal velocity. So we solved the equation F equals ma. But for F, we put in all the forces, or at least a couple of forces that we know the object will be subjected to. One is the force due to gravity, and the other is the resistive force. Now the force due to gravity is well known. The mass times acceleration due to gravity. Fine. But the resistive force we didn't know. And there were three suggested models. One is that it's proportional to velocity, or velocity squared, or the square root of velocity. We chose two of them, and we solved one using an integrating factor, and we found the steady state solution. The steady state solution is gm over k. Right? We know that. and that steady state solution is the equilibrium value. That is the velocity that is approached asymptotically. This is the terminal velocity. Now, if we use the other model, or rather when we use the other model, that the force, resistive force, is proportional to velocity squared, then we come up with a different result. The terminal velocity is the square root of gm over k.